This video presents ANIARA project, automation of network edge infrastructure and applications with artificial intelligence. My name is Ali Balador from Ericsson Research, Sweden, and I'm the project coordinator for ANIARA project. The content of this video has already been presented in AEIC 2022 conference in Belgium. To talk about ANIARA project, ANIARA has already started in June 2021 and will run until end of January 2024 with a budget of around 11,000 euros, which is equal to around 81 person year efforts. We have 20 partners from 3 different countries: Sweden, Germany, and UK. You can see the list of, you can see all the logos of our partners in ANIARA project on the right side. The project is funding by 3 countries, 3 national funding agencies, Vinnova from Sweden, BMBF from Germany, and also Innovation UK from UK. ANIARA project focuses on 3 different topics or 3 different concepts: 5G connectivity, edge computing, and artificial intelligence. The project provides enablers and solutions for high-performance services deployed and operated at the network edge. To manage this complexity, we need to take advantage of artificial intelligence to complement traditional optimization algorithms. The project also analyzes requirements and develops methods to minimize energy consumption. Here you can see the high-level architecture of ANIARA project. We start from the bottom of this architecture, which includes energy-efficient micro-edge data centers, and you can see also the power distribution and then the power grid. We also work on edge platform infrastructure and services. We are working on lightweight and portable runtimes, fast feature stores, and so on. The other things that we are working on is edge AI concept. We are working on intelligent feature selection, service performance prediction, and so on. Alongside, since we are talking about both the edge level and also edge cloud environment, we also need to work on management and orchestration of resources within this edge cloud environment. That's why we have this yellow box here focusing on this activity and these kind of topics. And then at the end is the applications that we cover in this project. The application and use cases that we have in this project can be categorized into 2 categories: a smart manufacturing and also a smart cities. And then the project develops different type of demonstrators for different use cases that we have in these application domains that will be provided and will shown at the end of the project. To give you a bit more information about what we have done during the first half of the project. Regarding the edge platform and infrastructure that we are working on it and we are developing within the project, we started with some challenges, and then the challenges in this case was edge deployments bring new challenges related to heterogeneity, resource constraints, and distribution. Which makes some of the solutions developed for data center oriented infrastructures not enough and adequate for to be used at the edge. That's why our objective in this case is to simplify the development and deployment of applications on distributed and heterogeneous sites. What we have done so far was we had some colleagues, and we had people within the project focusing on developing portable execution environment for the edge-based on WebAssembly or WASM runtime. We demonstrated for the halfway review of the project that a low footprint of WASM can be, as an execution environment, can be even run on a thin C device with 1024 kilobyte of RAM. You can see a picture of our demonstrator on the right top part of this slide. Before doing this, we also did a kind of like a pre-study to look at different solutions to provide this portable and this portable execution environment. As you can see on the right middle figure, we studied different solutions like containers, virtual machines, JVM, and so on. And we considered different parameters, like they should be able to run on low footprint devices, how they should be lightweight, isolation, language independent, platform independent, openness, and maturity. And then we realized that WASM, and then we actually selected WASM as a promising solution, and the solution that we want to use for computational offloading in this case. We also demonstrated full deployment flexibility. Same code module written in language of choice can be used across different software or hardware environments to offload modules between a device and the edge. Apart from this, we also had colleagues from HopesWorks developed a fast feature store for the edge, integrated with module serving on Kubernetes. They extended the HopesWorks feature store with real-time model serving with Kserve, enabling models to be deployed on Kubernetes containers at the edge. Related to edge AI, the challenge here, the challenge that we selected in this project is that the AI algorithms need to be tailored, especially for the edge infrastructure, compared to since previously these AI models have been running on the cloud, and now they need to be modified or tailored to be used at the edge level. The solutions that we have been working on it so far in the project was the methods for ML, machine learning, and model management based on transfer learning, resource selection, with the aim of ensuring high performing models that are continuously updated and correctly deployed. And also methods for selection of metrics to monitor in the 5G edge cloud with the objective of reducing monitoring overhead as well as optimizing model performance. And also leveraging and exploiting the distributed nature of data creation and decision making in edge cloud through distributed machine learning. In this case, service performance prediction based on edge statistics available to an operator has been selected as a use case for these studies. For more information, you can check the two papers that we have published in 2022 on the bottom of this slide. For the related to edge and cloud orchestration, we also focusing on shared protection algorithms. The challenge here is that orchestrators run resource allocation algorithms to select the most suitable set of resources to satisfy the client's needs. Backup resources are required to protect against link or node failure. These backup resources can be provided, provided and dedicated for each slice, or they can be shared between different slices. Different techniques for backup protection of optical network resources have already been proposed, including the ones that I mentioned: dedicated protection. So they dedicated dedicated backup resources for different slides. That is called DP, and also shared protection, which is SP. These are the two common techniques for backup protection. Considering connectivity and compute resources separately for these algorithms may lead to impractical solutions, especially when resources are scarce. Our solution in this project focuses on the dynamic slice provisioning, where both type of resources are jointly allocated. We developed a heuristic-based shared protection to encourage sharing of backup connectivity and cloud resources. We also evaluated these against a dedicated protection scheme using a Python simulator. Results show that the shared approach reduces the blocking probability by order of magnitude, and is especially beneficial when in-node processing resources are scarce. For more information, again, you can check the links on the bottom of this slide. Last but not least is our activities around edge cloud power management. The challenge in case of power management is installing thousands of edge data centers, primarily in cities, will require significant amount of power. However, many power grids are already utilized close to 100%. To maintain high availability, the edge data centers need to be complemented with alternative power resources and proactive power management systems. This requires specific hardware solutions integrated with the power grid, and also on-site power generation, supporting active load balancing by going off grid for shorter period of time. As you can see, the right figures in this slide, an edge testbed with Rise Ericsson as a collaboration of Rise Ericsson and Telia has already been provided. You can see in the picture on the top right that is connecting the edge data centers, cloud data centers, which is called ICE, running by Rise, and also Telia and Ericsson. They provide the connectivity to the industrial testbeds that we have in the project. And on the bottom of on the right bottom of this slide, you can see the edge data center infrastructure demo that has been developed by the partners in this activity within the project. So the main activity and the main solution that we have working within this activity or work package in the project was focusing on designing and implementation of a series of micro edge data center demonstrators for deployment at industrial sites. As a conclusion and wrapping up this video and my explanation about the ANIARA project, ANIARA provides different technology enablers supporting automation of network edge infrastructure and applications, including lightweight and portable execution environments using WebAssembly, heuristic-based backup, shared protection of optical network resources, ML model management based on transfer learning and source selection, feature selection for lowered network overhead and improve model performance. We have measurements from multiple points in the network and also can run machine learning models across the edge. And also micro edge data center demonstrators for deployment at industrial sites. Thank you very much for watching this video. If you want to get more information, you can check the project website, and also you can follow us on Twitter and LinkedIn.